Second?
Yes.
Dave, you have yours? Maybe? Oh, yeah. Emily? Okay. So here we go, folks. Did we do number 7? I thought we did. Oh, yeah, sure. Well, number 8 is identical. Let's just look at number 8.
Okay.
It says here,
Which factor do you college?
it's the one that says 3.0 at the top.
Okay.
No, you have it. It's the one in the middle. Yeah. So in number 8, it says, here's a polynomial. And first of all, folks, notice that with the polynomial, you can say y equals, but you can just as easily say f of x equals. Those two notations are identical. Well, I mean, they're not identical, but you can use them interchangeably. And it's going to be easier if we use function notation instead of y. But just, remind yourself that y is equal to f of x. Okay, so it says it describes the billions of flu virus particles in a person's body x days after being infected. So what does x represent?
The number of days?
Yeah, exactly right. So I would label it. I would always label my function so I know what I'm inputting and what I'm outputting. And therefore, the computation that I do, what is that going to be equal to? Billions of flu virus. Now you notice, I take these words right off the word problem. There's no decryption that has to go on here. You just take it right off the word problem. It says that it's X days after being infected, so X days, and then it describes the billions of flu virus particles, so there it is. So it says here, find the number of virus particles in billions after 1 day. So they told us the number 1. What do we do with the number 1? Do we plug it into the function, or do we set it equal to the function? They said
After 1 day, so your 1 day would be.
So the 1 is 1 days, or is 1 billions of flu virus?
What is y? Y.
Well, I mean, look at the number 1 there. What's the word literally that comes after it? Day. So we're definitely going to plug 1 in for x. There's no other choice, right? I mean, x is days, and they're telling us 1 day. So we're going to plug in 1 for x. And yeah, so that's not y. That's 1 is x. Okay, so then we're plugging that in. So negative 0.78 times 1 to the 4th plus 3.2 times 1 cubed plus 25.5. And you do all those computations on your calculator. It's nice that you're plugging in a 1 because 1 cubed and 1 to the 4th is just 1. So we're really just adding those together. Negative 0.78 plus 3.2 plus 25.5. And I get 27.92. Is that what everyone else got? So again, if my input was days.
That's billion, right?
Right, exactly right. This is billions of flu virus particles. And again, you just copy those words, billions of flu virus.
As sick as I thought.
Yeah, very sick. So the question was, find the number of virus particles in billions after 1 day. The answer is 27.92. Because they're asking for the answer in billions. Okay, so I hope that was a helpful discussion, especially the part about labeling your input unit, labeling your output unit, and then when they ask a question, they're going to give you a number, and you just have to choose, do you plug the number in, or do you set it equal to the number? And the unit will always tell you which one to do. In this case, it said 1 day, so we plugged in 1 for days. Okay, Emily, how do you feel about that?
Good.
Okay. All right, so the next couple problems are basically just kind of simple review problems, things you've probably seen in the past. Like in number 9, it says find the perimeter of the triangle. So first of all, what does perimeter mean? Yeah, the outside, right? And what do we do with the outside? Yeah, you would just add them all together. So we would just add all those together very carefully. You'd want to write down in any order you like. So negative x squared plus 9x plus 5x plus 9 plus 2x squared plus 8. And then whenever you're combining like terms, I really hope that you choose some sort of notation to use to identify and group similar terms. So like, I'm going to do an underline for my x squared terms. So what do I have? Negative 1x squared plus 2x squared? Which is 1x squared. And then I'll do a squiggly line for my x terms. So that's 9x plus 5x is 14x. And then I'll do a lightning bolt for my 9 plus 8, which is 17. Okay, so that's it. That's the perimeter. Now, at a glance, can you factor this quadratic? What multiplies to make 17?
1 and 17.
Yeah, just 1 and 17 is prime. And 1 and 17 don't add up to 14. They don't subtract to 14 either. So no, this problem is not factorable. If you wanted to find the x-intercepts, what would you have to do? You'd have to use the quadratic formula. Negative b plus or minus square root b squared minus 4a over 2a. All right. So that's that problem. You'll notice you didn't really do much, huh? It's not like you solved for x. It's not like you had to do any algebra. You just added everything together, and that was your result. Okay, next couple problems. Oh yeah, just 4 more problems. This is, again, just a review. And number 10, it says, multiply with distribution and then simplify. So how do we multiply 4x to the 4 times 2x squared plus 4x plus 2? What do we do? Exactly. So I hope you draw some sort of lines. I call those distribution lines. For fun, I call them rainbow lines. Whatever you want to call them, I hope you do them, because it helps the eyeball visually connect the numbers that you're actually multiplying. So, what was it?
I was doing this problem for online, and I had to do it. I had the problem correct. Well, at least I didn't know that until later. But yeah, he knows. I was doing the problem. I ended up having to do the problem 3 or 4 times. And what problem with me typing it in was I forgot an x.
Ah, that'll do it, won't it? Sure will. Okay, so I would multiply the numbers and then multiply the x's. So for instance, the first time, 4 times 2 is 8. And then what's x to the 4th times x squared? Here you want to be very careful because your brain has to switch.
You're adding
You're adding the exponents. It's very, it's tough because your brain is constantly switching between activities. On the one hand, you're saying 4 times 2, which is multiplication. But then x to the 4th times x squared is really x times x. And so you have 6 x's. And so then you add the exponents. That's something you might even want to make like a mantra to yourself. Multiply the numbers, add the exponents. Next one. Multiply the numbers, and then put a 1 right there, add the exponents. And then multiply the numbers, for instance, 8, and then add the exponents. Well, technically, what's that exponent? That's x to the 0, right? So then 4 plus 0 is still 4, so it would just be x to the 4. Okay, anyone, how do you feel about that? Is that okay? I think, I know that you've all seen that before in your life. It's just a matter of reviewing and being very careful, as Hector attests to, that dropping a single x out of it is going to make the whole answer incorrect. Okay, how about the next one? What's the, it says it right there, multiply with 4. So now number 11, we're going to do x minus 3 times 3x plus 4. Yeah, simple FOIL. Now, my approach is I just draw my lines and I just multiply everything. So I do FOIL, so first, and I draw my lines every time. I swear to you. I'm a professional. Okay, I can do these things in my head, but I don't because I want to make sure I get it right. And the minute you try to do it in your head, that's when you're going to make a mistake and get it wrong. So I draw my line. So x times 3x is 3x squared. Outer, x times 4 is 4x. Inner, negative 3 times 3x is negative 9x. And then last, negative 3 times 4 is negative 12. You can even draw the lines and still make a mistake. But I still think it's better to go this way. Now what else do we have to do? Yeah, combine like terms in the middle. So we have 3x squared minus 5x minus 12. Now, I have seen people do this. It's a really nice, pretty technique. I don't do it myself, but it's really nice looking. And that is, I see people write out FOIL. And they do one term at a time. They say first is 3x squared. And then they do outer is 4x. And then they do inner is minus 9x. And then they do last is minus 12. So that they can just see them all. I've seen some people do this. It's nice. It kind of lays all the information out there for you. And then maybe they group this together and they say, well, that adds up to negative 5x. And then they read off their answer. Anyway, I just mentioned this because there are lots of ways to do this. My biggest request is that you do some way. Right? Show your work. Don't just kind of look at it and write down your answer. Because that's when accidents can happen. Okay, that was number 11. Skipping number 12, because there is no number 12. How about number 13? What's 3x plus 7 squared?
Multiply those.
Yeah, you're technically multiplying 3x plus 7 times itself.
Yeah, so instead of writing the whole thing out, what I did is that I just said, what's 3 times 3, and then just add the exponent to the x, so 9x squared.
Mm-hmm.
Then 7 times 7 is 49.
Yeah.
Positive. And then the last part is kind of difficult because then you're multiplying depending. 3x multiplied by 7, you're going to get something x, so
21.
21x, and then add it together, so
21 plus 21 is 42.
yes.
Yeah. And what Hector just described is a way of doing the problem. And I'm assuming what you're doing there is trying to do the whole thing in your head.
Yeah, pretty much.
Right. So again, I advise against that. I really hope that you show your work and do it carefully. And again, show your lines. So first, so that would give us 9x squared. And then outer, so that'd be 21x. And then inner, that's another 21x. So yeah, Hector, you're getting all the right numbers. And then last is plus 49. And then you combine like terms in the middle. Now, this is a problem that is very, very, very often missed by students because they make the mistake of thinking that 3x plus 7 squared, that they can just square both of those. And that's not correct. If you just write down 9x squared plus 49, then you didn't do the FOIL process. And what is my answer missing? 42x.
Plus
Yeah. Is what?
Once it cancels out.
Right, unless it cancels out, but it'll never cancel out. If it's something squared, the middle terms don't cancel; they add together. And what's negative?
If one of the terms.
Right. Well, I mean, even if it was 3x minus 7 squared, it still is not going to cancel because with FOIL, you'd have 3x minus 7, so you'd have 9x squared minus 21x minus 21x plus 49. So those middle two terms don't cancel. What's the only time the middle terms will cancel? Is if one of them is positive and one of them is negative. Then the middle terms cancel because you'd have 9x squared plus 21x minus 21x minus 49. Then they cancel, but if they were opposite signs, you can't write it as something squared. Yeah. Okay, well, very good. This is the point of reviewing all of this, is just to check ourselves. So now everybody, you go ahead and do that last one on your own. 4x minus 3 squared. Make sure you write it out as 4x minus 3 times 4x minus 3. And then, yes, as Hector mentioned, you will have online practice on that. It's not due today because we didn't finish this last week, so you still have all of this week to do it. It's section 3.0, and it's going to give you plenty of good practice to make sure that you're doing all of this FOIL and distribution correctly.
3.0 was, do you remember?
Oh, well then let me fix that then.
Yeah.
Let me fix that again. Oh, in fact, I think maybe I did fix it. I'll fix it right now. Well, you all finish that problem. Alright. I thought it was going to be a lot farther than that.
He told us to not do it
Beginning
overnight.
of the class. Awesome. Awesome work. All right. Did you get 16x squared minus 24x plus 9? Is that what everyone got? Let's check. You got 16x squared minus 24x plus 9. Is that what everyone got? Okay, super. Now, Hector, I appreciate, again, your desire to do things without writing down the work you say. It takes up time that you don't have. And if you can do it, then just do it. Why do you have to show all the work?
Did I say that out loud?
You did. You did. And that's fine, because I appreciate that. I don't want to take more steps than I have to, especially if somebody else is telling me to do steps, and I'm like, I don't have to do those steps. I can just do it like this.
I'm not saying they're bad. I'm not saying it's good. It's good to learn them.
Yeah.
If you're taking a test and you're strapped for time, if you already know something, then I would recommend just writing down the answer and then move on to the next problem so you can complete the whole thing.
Sure.
And
And so
the way
ways
I
is
the way my
trade-offs.
early instructor did it is that any problem that did not have anything written down was kind of
And that's basically how I grade too.
yes.
You know, like if it's worth 5 points and all you do is write the answer, I'll give you 1 point.
It's,
Even at best is 1 point. But at the same time, sometimes you do things over and over and over again, and yeah, I can just look at that and write down the answer. And there's little tricks you can do in your head to try to do these things. But still, we try to pretend that somebody's life is on the line, and we don't play casually with people's lives. We want to get the right answer for sure. Okay, so all done with 3.0. Let's move on ahead and talk about 3.1. We already overviewed this material, so I'm just going to go ahead and call out some of the material in the packet and verify what we know. Now, when they give big old things like this, there's lots of information. I'm not necessarily going to sit here and read through all of it. By all means, you can go back and read through it. But it's basically just a list of definitions and formulas, and we'll use them as we need them. So, first of all, end behavior. We talked about end behavior. What is the end behavior of any polynomial with an even exponent? What are we going to call that end behavior? So, end behavior. What if the end behavior, well, what if the first term, okay, the leading term, is a positive x to an even number? What will the end behavior look like?
Positive.
Yeah, it'll look parabolic, right? The two tails will be pointing up to infinity. And then if the leading term is a negative x to an even power, then it'll be a parabola facing down. And you'll have the two tails pointing down to infinity. So that's if the leading term is an even exponent. It doesn't matter if it's x squared, x to the fourth, x to the sixth. If it's positive, it's parabola facing up. If it's negative, it's parabola facing down. The word parabola is reserved for x squared. But we can call all of these parabolic, or we can just call them U-shaped. Okay, whereas end behavior for an odd function, so if we have a positive x cubed, what you have is a smiley face to the right and a frowny face to the left. That is basic cubic behavior. Again, we call it cubic. This is the only function that's a cube, but x to the fifth, x to the seventh, x to the ninth, you can still call them cubic in terms of their end behavior.
it's any number that's odd.
Any number that's odd. Oh yeah, sorry, I shouldn't put a 3 there, I should write odd. Thank you. Okay, and then if you have a leading term which is a negative x to an odd number, then you basically flip that upside down, and it'll be a smiley face to the left and a frowning face to the right. There's only those end behaviors that you have to memorize to know what that is going to look like. So that's our end behavior, and you know end behavior by looking at the leading term. Look at the leading term.
So the x squared on my end behavior was what, 10 or 5?
Yep.
No matter how many ups and downs there are, as long as it's the same like this,
Exactly.
it doesn't matter. It's
Yeah.
still odd.
Basically, if
Still
you
that.
zoom out far enough, in fact, here I have an example right here for you. So I have this graph right here, folks. Take a look. See how nice and wiggly it is? Well, if I zoom out far enough, your eyes can no longer really see the wiggles. And what do we have? I've got that graph right there. So when we talk about end behavior, we mean zoom out really far and just think about where the tails are going. You've got a tail going up to the right and a tail going down to the left. Yep. Yeah, really good question, folks. All right, so that's what's called end behavior. And otherwise, let's definitely do number 1 and number 4 to get ourselves a really good idea of what we're trying to accomplish. Right, now, it says all sorts of things in the instructions. It says find the degree, the leading term, the leading coefficient, the constant term, and the end behavior. Sketch a picture. So here's what we'll do for number 1. Go and jot down f(x) equals 3x to the 5th minus 2x squared plus 1x plus 1. And let's identify all this information. So first of all, find the degree. The degree is the highest power on x. So that's the number 5. The degree tells us many things. It's the highest power on x. It's telling us about the end behavior. So I could go ahead and also jot down degree. I'm going to write down end behavior. Because it is telling me that this is an odd graph. But that's also telling me what about the x-intercepts? There is at most 5 x-intercepts. There's a maximum of 5 x-intercepts. So the maximum x-intercepts, maximum number of x-intercepts. So wow, that leading term exponent, the highest exponent, has a lot of information, doesn't it? Okay, so that term in and of itself, that whole thing is called the leading term. Because the exponent on x, the highest exponent on x alone doesn't tell us the end behavior. We also need the number out in front, which is a positive 3. So this whole leading term is telling us about end behavior. The exponent just tells us what the shape is, but whether it's plus or minus tells you if it's facing up or upside down. So now we can go ahead and say that that 3 is the leading coefficient. The leading coefficient just basically tells you if it's facing up or facing down. Like the parabola, is it facing up or is it facing down? It's positive facing up, negative facing down. Okay, so we have the degree, the leading term, the leading coefficient. What's the constant term?
The leading term, you took the leading term as everything, right?
Leading term is the whole darn thing together, yeah. So what's the constant term? Because this is a variable term, this is a variable term, this is a variable term, this is a constant term. Because it's just a 1. No matter what I plug in for x, this is just going to be a number. It's the constant term. And it tells us some really helpful information. If the first term tells us our end behavior, the last term tells us what? No, say it. Yeah, beginning, I think I know what you mean by that. The last term will always tell us the y-intercept, exactly, which is where you could say the graph begins, especially if you're drawing a line. You plot the y-intercept and then you draw a line. So yeah, that is the constant term, is the y-intercept. And why is that again? Let's remember, one of the most fundamental ideas that we've talked about in this class so far is that if you have a function, f of x, then f of 0 is the y-intercept, and anywhere f of x equals 0, x is an x-intercept. Right? I mean, this would be something good to tattoo on your body somewhere. Like, it's such a key idea in mathematics. So you've got the y-intercept, you've got the x-intercept. So this last term, if I plug in 0 for x, then that term becomes 0, that term becomes 0, that term becomes 0. And so you have f of 0 equals 1. So therefore, yes, that's the y-intercept.
That is y-intercept, but so the exponent is odd. So yeah, the exponent is odd, so we got something like this, not like this.
Yeah, yeah.
And the leading term is also positive.
Yeah, yeah. So it's that.
Yeah, it's going to be that.
Yeah, with a y-intercept of 1 so far. Okay, that's what we know so far. And then finally, oh, the end behavior. Okay, so we're ready now. For number 1, we could make a really basic sketch, and I mean really basic, because all we really know for sure now is that my end behavior is an odd behavior going something like this. And we also know that I have a y-intercept at 1. That leaves a lot to the imagination. Like, what on earth is happening in between? A lot of things could be happening. First of all, how many times could it be crossing the x-axis? At most 5. So, I mean, the graph could go like this. It could go 1, 2, 3, 4, 5. It could do that. And notice I went through my y-intercept. It doesn't have to go like that, though. What's the fewest number of x-intercepts we could have? What's the least number? 2.
1.
Yeah, 1.
1, because it could just cross through once and then leave. Right? Could we have 0 x-intercepts? That would be impossible. That would mean it's just jumping from one side to the other. Okay, and polynomials don't do that. Polynomials are smooth, continuous graphs that you can always draw by leaving your pencil on the page. There's no picking up of your pencil around. Okay, well, that's all we know so far. That's all we know from problem number 1. So now let's look at it from a different perspective. Now, I wrote skip on these. We could just quickly analyze them. Like, what's the end behavior of this one? Now, notice they wrote the terms out of order. What's the first thing you have to do? You have to put the terms in order. So let's just look at the leading term. It's a negative 3x squared. So does it look like this, or does it look like this? Yeah, it looks like this. Yeah, it's an upside down problem. Now what about this last one? It's also written out of order. You'd have to write them in order. What's the leading term? Negative b cubed. So what will that look like? What's my end behavior? Yeah, that one. So it'll look like this. Okay. Now, let's come on down here to number 4. I'm going to erase just a little bit of my graph so I have room. Okay, now, What we just did was we analyzed a polynomial that was an addition problem. So if you don't mind, I'm going to refer to this polynomial as an addition problem because it's something plus something plus something plus something. You can also call that expanded. That's an expanded polynomial.
You want us, because you're going to be giving this to us back for a grade, you want us to,
You just cross out
graph?
2, 3, 5, and 6.
no, I was going to ask, you want us to just write a graph on this, or you want us to like put the like infinities plus and things like for the
Well, you don't have to do that like it's on the more program.
Okay.
You can just write down exactly what happened. Thanks. Does that answer your question? Yes. Okay. Okay, so now number 4, that's a factored polynomial. So if we write that one down, h of x equals x minus 1 times x minus 2 times x minus 3 times x minus 4. This is not an addition problem. This is now a multiplication problem, which again is our whole goal. This is a multiplication problem. We call this factored. If this one is called expanded, this one is called factored. Our whole goal is to get it into factored form because then we can use the zero product rule, which says that if I set this equal to 0, then this and this and this and this equals 0 only if each and every one of those could be equal to 0. And that's how you find your x-intercepts. You don't plug in 0 for each one. You set each one equal to 0.
Oh, okay.
Yeah. If right now I plugged in 0, what would I find?
Positive 1, positive 2, positive 3, and what? Positive 4. Well, that's 50.
Not positive. I'm not sure what you were just saying. But if I
Like,
plug,
like I was making x like.
oh,
x
that would be if you
minus-
set each one equal to 0.
Yeah.
Yes, correct. But so right now though, if I plug 0 in, first of all, if I plug 0 in, what am I about to find? The y-intercept. And what do we end up doing? We just take all those numbers as they are and multiply them. So what is the product of a negative times a negative and a negative times a negative? So this whole thing's gonna be positive. 1 times 2 is 2, times 3 is 6, times 4 is 24. So I now know my y-intercept is 24. Now how did I get the y-intercept? I just multiplied the numbers as I saw them. So that's a good rule that you could follow. How do you get the y-intercept from a factored form polynomial? You just multiply the numbers as you see them. You don't change the signs. Right? What Hector was doing by changing the signs, he was finding the x-intercepts. To find the y-intercept, you just multiply the numbers as you see them. Now, this brings me to an idea that I want to share with you, and it's called lazy person's FOIL. Did I already say this? The lazy person's FOIL. See, if I actually wanted to FOIL that out, it'd be very laborious and time-consuming. First, I'd FOIL x minus 1, x minus 2, and that'd be x squared minus 3x plus 2. Then I'd have to distribute that with x minus 3. And then I'd have something terrible. I'd have x cubed minus 3x squared plus 2x minus 3x squared plus 9x minus 6. And then I'd combine all those terms, x cubed minus 6x squared plus 11x minus 6. And then I'd still have to multiply all that together with x minus 4. So then when I do all that, I'm going to end up with x to the 4th, and then a whole bunch of things plus 24. Do you agree with that? Yeah. Forget all those middle terms. If right now I just FOILed and I did the x times the x cubed, that gives me the x to the 4th, my leading term. If I do negative 4 times negative 6, the last terms, that gives me the 24, which is the y-intercept. That's all we want to take away from this process, is that if you're given a factored form polynomial, I'd like you all to know how to do the lazy person's FOIL, which you just multiply together all the first terms. So x times x times x times x is x to the 4th, plus dot, 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 dot. And then just multiply together all the last terms, which we already knew was 24. What's nice about this is that we now know the first term is our end behavior, and the last term is our y-intercept. Now this is why factored form is so great, because if somebody just walks up and gives you factored form, you already know the x-intercepts, which Hector already said for us, the x-intercepts. We're simply changing the sign of all of those, 1, 2, 3, and 4. By doing the lazy person's FOIL, we know the end behavior, and we know the y-intercept. So we now know everything we need in order to graph this. By the way, is everyone comfortable with where we got the numbers 1, 2, 3, 4 for the x-intercepts? Because we're setting each of those factors equal to 0. And if you set it equal to 0, you have to move the number over and it changes the sign. Okay, so now let's make a graph. Notice how much better this graph is going to be. I didn't have to graph the left-hand side. All my x-intercepts are on the right. So watch how this works. I'm going to have my x-intercepts of 1, 2, 3, and 4. I put a little dot at each of those because I know I have an x-intercept there. Now, what was my y-intercept again? 24, so I'm going to put a little dot there called 24. Yeah, it's an even end behavior, so I'm going to go ahead and draw a picture of that. It should look like this. And so here's what you do. You're going to have two tails pointing up. You put one tail on the far right-hand x-intercept. You put the other tail on the far left-hand x-intercept. You attach the tails to the rightmost and the leftmost x-intercept. And then at this point, you connect the dots. And you say, connect the dots, blah, blah, blah. So where does this tail go through? It goes through 24. And then the rest, you just slice, 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 and you connect it all together. Slice, 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 slice. And that's our graph. That's a really good looking graph. For not using a graphing calculator or Desmos, that's an amazing amount of knowledge about what's happening here. And just imagine if you really wanted this graph to look good, you're just a couple tables of values away. Like you'd like to know how far down does that little dip go. So you could, roughly speaking, plug the number 1.5 in, and that would tell you how far down that dip goes. If you want to know how high up that goes, you could plug in the number 2.5 and find out how high that is. Then if you want to know how low that goes, you can plug in the number 3.5, and that would tell you how low it goes.
But 1 3/4.
Well, no, that's a good point. See, the lowest point and the highest point and the lowest point aren't necessarily halfway between 3 and 4. I'm just saying halfway as a rough estimate. Right? The actual lowest point could be a little bit skewed right or left of the middle. In fact, it probably is. But just roughly speaking, if you plugged in 1.5 and 2.5, 3.5, at least it's giving you a gauge for how high those peaks are. Okay, number 5 and 6, definitely you can just cross out. We're going to see problems like those later on. And, we'll do those later. So how does everyone feel about expanded form and factored form? Just the information that we can extract. You notice that we haven't done a lot of work yet. We're just extracting information, and we're recognizing the information. Okay.
So when it's asking for the end behavior with factored form, we can just do that, but we don't have to do the whole entire thing.
You do the lazy person form. Yeah. In the last class, earlier this morning, I referred to the lazy person foil. Somebody raised their hand, they're like, do the lazy man's foil. I was like, oh, it doesn't have to be a man or a woman or anywhere in between. It's just a lazy person. But then I realized I shouldn't even call it lazy. Is this actually lazy? No, this is actually very efficient.
Do Hector's foil.
Yeah, we could call it Hector's foil. Not because Hector's lazy. Yeah, but because you just want the information that you need. And that's the only information you need. You don't need to FOIL out all those middle terms. You just need the leading term, and you just need the constant term. Yeah, so it's not lazy, it's efficient, it's Hectorish. Okay, very nice, folks. Let's go ahead and keep on going.
I heard something about NASA hires lazy people because lazy people think it's the most efficient way to do something.
Yeah, well, that could very well be. Okay, again, all interesting information. You can go back and read it later. We're going to keep going. So, it's going to give us now an opportunity to do some of these graphs. And let's read the instructions. It says, find the real zeros. Again, what does the word zeros mean? It's the x-intercept. Instead of the word zeros, why don't you underline or circle the word zeros and write x-intercept or the word roots? Because you should be familiar with all of those words. Roots, x-intercepts, zeros, solutions. So find the roots or the x-intercepts of the given polynomial and their corresponding multiplicities. We have to define that word multiplicity. And then use that information along with a sign chart. We're not going to do a sign chart. We're just going to use this information to sketch a graph. A sign chart is another way to sketch a graph, but I'm showing you a way to sketch the graph, which I personally like better than a sign chart. Okay, so we have our first function there, number 1. And it's the function a of x equals. Now, as we start to write this down, I can just write it down as it is. X times x plus 2 squared. This x kind of looks a little weird because we're supposed to have factors. You know, x plus or minus a number, x plus or minus a number, x plus or minus a number. How can I rewrite that to fall in line with everybody else? Yeah, I can write x minus 0, I can write x plus 0. It doesn't really matter, but just put a 0. Whether you write x minus 0 or x plus 0. Put it in there so you see it. Okay, now next, that is an exponent of 2. What's this exponent? 0. Now, if it was 0, Anything in the power of 0 is 1.
Or
I
one.
just,
It would just go away. Yeah, Hector?
do you think because you put a negative with the zeros, that means that you should change the sign at all?
No. It's a good question, and you should check for yourself, but no, it will not. Okay, now wait. Did everyone feel okay about the 1? Okay. Because there's always an invisible exponent of a 1 in anything. Okay, so now we have this. Now let's go ahead and define multiplicity. The exponent on the factor is the multiplicity. So multiplicity is the exponent on the factor. So for instance, if we now go ahead and list out our x-intercepts, so the x-intercepts now we can read them straight out. We have an x-intercept at, well, yes, 0. We have an x-intercept at 0, and we also have an x-intercept at -2. So the x-intercept 0 has multiplicity 1. I'm not going to write multiplicity. It's a long word. I'll write multi. Whereas the x-intercept -2 has multiplicity 2. Now, right now, this just seems like a really silly extra vocabulary word, right? Why do we even have the word multiplicity? It's just the exponent of the factor. Well, we get really interesting information from looking at the multiplicity. The first thing that matters is that if I actually now write this out fully factored, because let's remember, we want to do the lazy person's FOIL. And to do lazy person's FOIL, it's not actually convenient to have it squared right there. It'd be more convenient to actually write out every single one. So the lazy person FOIL, we're going to write out x minus 0, x plus 2, x plus 2. Because now that will allow me to actually multiply all the first terms, multiply all the last terms. You can't do that with a 2 right there. It needs to be written out. So x times x times x is x cubed. And then the last term, 2 times 2 times 0, 0. So in other words, our end behavior is an x cubed, which looks like that. And our y-intercept is 0. No. Yeah.
Can you explain to me that why
Yes.
0 has a
Well, right here, we're referring to this as each of these factors is an x-intercept.
Yeah.
So, and the power on that factor is 1. So the x-intercept 0 has a multiplicity of 1. It just means that the factor has an exponent of 1.
And then why negative 2?
Because one of the x-intercepts is -2. Because remember, to get the x-intercepts, you have to actually take that and set it equal to 0.
Yeah. Oh,
That's the zero product rule. Does that answer your question?
yeah, it does.
Okay, so notice now, it was really helpful to actually put in the x minus 0 and then expand it all the way so that you can more clearly see by the lazy person's FOIL that the leading term is x cubed and the final term is 0. Because if you just looked here, you might have accidentally said, oh, the y-intercept is 2 times 2, which is 4. But there's actually a 0 term in there. Okay, so now we can make our graph. Now here's where it gets really exciting. To make our graph, we have an x-intercept at 0. We have an x-intercept at -2. We have end behavior, which looks like this. So I'm going to draw my tail going up to the right of the rightmost x-intercept, and my tail coming down from my leftmost x-intercept. Now here's where multiplicity actually matters. Well, multiplicity already mattered to allow us to calculate the correct end behavior and the correct y-intercept. But here's what really matters about multiplicity. If you have odd multiplicity, and I'm going to go ahead and write this out right here. So multiplicity, odd multiplicity refers to when you draw your graph, you draw a slice. And even multiplicity, you draw a bounce. Let me describe what that means. Almost always we draw a slice. So you'll notice that up here I went slice through the x-axis, slice through the x-axis, slice through the x-axis, slice through the x-axis. A slice is just passing through it. So you start above it, and then you go below it, and then you start below it, and you go above it. And you're above it, you go below it, and you're below it, you go above it. So slicing through the x-axis means you're starting on one side of it, and you're going to the other side. Whereas a bounce, now everybody watch as I do it on this one. 0 had a multiplicity of 1, which was a slice. And negative 2 is a multiplicity of 2, which is an even number, so that's a bounce. So I'm going to go ahead and write down on my x-intercept, negative 2 should be a bounce. I'm going to put B there for bounce. And 0 should be a slice. I'm going to put an S there for slice. And watch how I do this. I'm coming up with my tail, and I'm not going to slice through the x-axis. I'm going to bounce. And then I'm heading back towards that one, and I am going to slice through. And that's what that graph looks like. So when I use the word bounce, I mean that your graph bounces off the x-axis and comes back down. So it started below and it stayed below. Whereas the next one was a slice, so I passed right on through.
It's a positive negative. That's why it's positive.
Because the exponent was even, it bounced. And in fact, you can go right here. If you see an odd number, it's a slice. If you see an even number, it's a bounce. Yeah, I would find it helpful to label it right there on the factored form immediately, and then label it again on the graph so that you know you're actually doing it correctly.
I always thought of it as a open or closed valve.
Open and close what?
Valve.
Oh, tell me more about that.
So like when you have, well, when you turn on you turn on your faucet, right? It goes straight through. So that would be considered an odd. So when you close it off, it like stops or bounces away, which is an even. So whenever you go through a certain point, an x-intercept, depending on what the power is, tells you whether or not it's going to be a closed valve or open valve.
Oh, that's very interesting. I like that. That's a great analogy, Lee. I've never heard that. So everybody, as an example here, look at my graph here. First of all, what are each of these x-intercepts right now? Are they a slice or a bounce?
Slice.
Like this one's a slice, it goes straight through. This one's a slice, it goes straight through. This one's a slice, it goes straight through. This one's a slice, goes straight through. And that one's a slice. Now look at all my exponents. What were all my exponents? Yeah, they were all 1. Let me go put them in there to be very clear about it. So by typing to the power of 1, I'm not changing my graph at all. You'll notice the graph is still the exact same. Now, watch, because this is super fun. I'm going to change my graph. I'm going to change what my graph looks like. Right here at -5, I'm going to put a bounce by just changing that 1 to a 2. And then, boom, it just bounced. Now the whole graph changed, right? Because I just changed my end behavior as well. I put in an extra x term, so that changed the end behavior. But the key thing is, notice now, it goes bounce, slice, 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 slice.
Would it change if you put the exponent with a higher number too?
Yeah, so now watch just what happens when I put in a 4. So 2, any even number, right? So here's a 4. Oh, that's a 24. 4. There's a 6. There's an 8. And there's a 10. There's 12. What's happening to that particular bounce?
It's getting wider.
Yeah, it's getting wider and flatter, isn't it? But let me just go back to a 2. Just making it an even number makes it a bounce. Okay, now watch. I'm going to take my x-intercept at 0. I'm going to make that a bounce as well. So now, do you see how it's slicing through the x-intercept at 0? I'm about to change it to a bounce. Kaboom. Now it's bouncing off of 0. Now again, look. I got a bounce, a slice, a bounce, a slice, a slice. So let's change one more of these to a bounce. I'm going to change the x-intercept at 3 into a bounce. So I'm going to change that 1 into a 2, and it's a bounce. Now this is where you can have a ton of fun, because watch, what if I just change them all to a bounce? I'm just going to make the whole thing a bounce. And it'll go bounce, 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 bounce. And I'll fix my window too, so it looks a little better. Ooh. There we go. There. So every single one of them now is a bounce. It never goes below the x-axis once, because I just went bounce, bounce, bounce. That would be a really weird bouncy ball. That's really actually how a football bounces, isn't it?
Looks like flubber.
Yeah, like flubber. Yeah, footballs bounce in weird ways. Okay, so now, that's what the word multiplicity means. Multiplicity, if you go back now to how we've defined it, multiplicity is a lot of things. Multiplicity is the exponent on the factor, which tells you if that particular exponent bounces or slices. That's multiplicity. That's what it means. So now that we've seen how to do that particular problem, we're done. Let's try number 2. So number 2, we're going to start by writing out the function. So f of x equals, is that a -2? -2, and that's x minus 2 squared times x plus 1. Now, where to begin? We have a lot to do. We have to do the lace person's FOIL. We have to think about multiplicity, which, by the way, I put a 1 there, because it's an exponent of a 1. It's not listed. I think we might as well start by labeling the multiplicity. What is the 2? Is it bounce or slice? Yeah, that's bounce. And the 1? That's a slice. Okay, so I already know that. Let's go ahead and do the lazy person's FOIL. So we've got -2 times x minus 2 times x minus 2 times x plus 1. Right? All I did was write the x minus 2 twice. Because in order to do the lazy person's FOIL, you have to see every single factor. Okay, I'm going to leave the -2 out front for a second. I'm going to do lazy person's FOIL. So I've got x times x is x cubed, plus a whole bunch of terms that I don't care about. -2 times -2, positive 4, 4 times 1 is 4. So there's my lazy person FOIL. But now I do actually have to distribute in my -2, because that's part of it. So now my just distributing, the first and last, I have -2x cubed, plus a whole bunch of terms I don't care about, minus 8. So what do we know so far about our end behavior? What does our end behavior look like? Which end behavior is it?
X.
Yeah, it's a negative cubic. So I would draw that right now, just to remind myself. That's the end behavior I expect later on. The y-intercept is already there. I just labeled it. The y-intercept is -8. Now we want to think about our x-intercepts. We just have the 2 x-intercepts. Keeping in mind, even though there's 3 factors, that factor is listed twice. It's still just representing 1 x-intercept. So where are my x-intercepts? Yeah, my x-intercepts are at 2, and that was a bounce. And at -1, and that was a slice. Now keep in mind, if you wanted to say with the multiplicity, you'd say the x-intercept 2 has a multiplicity of 2, and the x-intercept at -1 has a multiplicity of 1. We're much more interested in the words bounce and slice, because that's telling us how to graph it. Okay, we now know everything we need to know to make a graph. We can now make a really good-looking graph. Before I make the graph, what questions do you have? Valeria, Emily, Olivia, Malaria. I'm just trying to join your names. Question? Hector?
Wouldn't it be, I was saying, before you do this, wouldn't it be a good idea to rearrange them so it's like goes by order?
Well, it is always nice to rearrange them in order. Yeah, I agree with you. Like there, I could have listed it from negative to positive. That's a good idea. Okay, so let's draw them. I've got an x-intercept.
Rewriting the whole, like at the start of it, or rewriting the top.
Oh, I mean, if you wanted to, you could. Yeah, you definitely can. Okay, so my x-intercept is at -1. At 2, now I'm going to go ahead and write it. -1 is a slice. There's an S. -2 is a bounce. There's my B. There's my dot. There's my dot. I've got my end behavior. So for my leftmost x-intercept, I put my tail going up. For my rightmost x-intercept, I put my tail going down. I also know my y-intercept. My y-intercept should be here at -8. And it's at this point that you just start connecting the dots, making sure you do the proper slices and bounces. So take a look. As you come from this tail, I always like to go from left to right. So I'm coming down my tail. I slice through the x-axis. I have to go hit through that y-intercept. Then I'm going to come back up and have to bounce off of that. And there it is. And when you're done, just verify that everything works out. Did you slice through that point? Yeah. Did I bounce off that point? Yeah. Did I hit my y-intercept? Yeah. Just think, all those connect the dot workbooks you did as a 5-year-old. Someday, you're going to have to connect the dots on a graph. Do you think that's why there's a connect the dot book for 5-year-olds? I don't know. All right, well, we did it. Now, of course, you might be curious, are we right? That's always a good question to ask. Whenever you're done with anything, it would be very natural and appropriate to ask, did I do it correctly? And you can always just check your work by going on over to Desmos or your graphing calculator, typing it all in, -2 times x minus 2 squared times x plus 1. And as always, when you're doing your graph, you got to spend some time fiddling around, find a good window. Like right now, my window is kind of tricky. I don't see what I want to see, do I? My scale is way off. My Y scale is 500,000. So I need to change my Y scale to be back at something normal, 10 and 10. Oh, my X scale got really messed up. Let me change my X scale. So negative 10 to 10. Oh, now we're looking good. Oh, now we're looking really good. Yeah, that's pretty good, right? I have an x-intercept at -1. My balance is at 2. How did we do? What's the only difference between my drawing and the actual graph? Let me expand my x-axis a little bit. So, -5. Yeah, in truth, it is bouncing off the y-intercept. It hits the y-intercept as the lowest point and then goes back up. Did my graph show that? No, I mean, you're off. I'm off a little. But you know what we call this? Good enough. All right? Like, yeah, I was off on that minor detail. And if somebody's going to give me a hard problem about that, oh, sorry, I didn't have that minor detail correct. The key is that I got my x-intercepts, my y-intercepts, and my tails. All right? That's what really, really matters when you make a sketch. Now, obviously, now that I know it looks like that, I'm compelled to fix it. No, I won't. Okay. All right, how does everyone feel about this idea of graph sketching? We are sketching a graph. As always, and I know I've said this before, we're learning the skills to do everything by hand, even though you can just look it up on a graph calculator. Yeah. Okay, well, let's move on. And now I know that there were more problems, weren't there? There was more right after that. Number 3 and number 4, and then I said to skip 5 and 6. So, oh, didn't my phone already go on? I think my phone already went on. So I tell you what, we don't have to do 3 and 4. You can cross those out. We can cross out that whole page. Okay, because we've done enough practice to see how it works. Plus, we're going to continue practicing more problems as we go. Or do you all want to see one?
No.
That's fine. That's totally fine. We can be done right there. So, perfect timing. My phone did go off, right?
Yeah.
Okay, yeah. So let's take a break. Let's come back at 1:46, and then we'll start up. There we go.
What's my?
Is it brand new? Yoga?
No, it's
I need to go get some water. Hydrated.
I know last night. Serious? Okay. And Tuesdays and Thursdays we have como 8 horas de trabajo plus los lunch hour porque sí. Tengo que siquiera I didn't know it. Didn't I notice it? Oh no, I just have but that's remember when I don't think that for my like I'm looking. I wish I could forget home and do. Why are you so sleepy? Me? Yeah, because I've been working late. See? I get at 1 and then I have to wake up at 5. Oh, you too. You have a problem? I am. With the problem of having like
car,
I'm
then you fall asleep.
No,
I know, but it's better to have a car where you like wake up early. Yeah, that's why I'm there.
You know, something must be traffic. Really?
Yeah, and then you have to deal with traffic.
to do like.
There's no traffic when you walk.
Where do you work at?
I'm coming down. The one in 36th Street.
You live in the streets. Is it your first job?
No.
Do you like it?
No.
No.
It makes me so tired. Really need to stand 24/7.
You work full time? And they give you 15-minute break? Wow. That's bad. I thought you were supposed to only have 30. Yes. That's what I thought.
And
Isn't
sometimes
it?
we don't even
If
get
you work an 8
I
hour.
do construction, so I wouldn't know.
Anyways, you did your the construction, but you took a break. Like, no.
Sometimes we don't take breaks, it depends on the person. If you're hungry, you eat.
Well,
If you're not hungry, you don't take part, you don't just keep going.
Well, my uncle, he owns a freaking company. He tells people. They even teach an hour sometimes.
My uncle runs a landscaping and cement company, which I've
That's good.
and cement work. So I do cement. I think it's cool, but it's not fun when you're wheelbarrowing at some pounds of cement. It's you think 50 pounds. You think 50 pounds is nothing to do when you're wheeling barreling cement, but the problem is it's still to the bag. You add water there, you're gonna end up spilling some.
What tomboy?
You're a tomboy? I've never heard of any tomboy with me.
Well, inside of me, like talking about hardworking, being like handy girl,
Okay.
Okay. I can do men's stuff. I don't know what I'm talking about. Like I'm gonna dress like a That's cool. I know, sir.
What do you do?
Right now I'm just going to school. I wish I could have that.
I only do that with my uncle every single other every other week. So
Oh, that's good. Oh,
we guess.
Well, I'm 75.
My phone go off when I like.
So you guys have updates.
Oh yeah, okay.
Got, was it one doctor last week? Didn't even have, so I had a slight concussion.
We did, I'm not surprised.
Yeah. And again, that's why I was like, why don't I have any coaching, like all these things as far as having trouble. I have a gift. It's like right here, like before I do the work.
You work every day?
Right now, it's like.
I'm looking for another
job.
No, I want to quit this job and then get another. They're considering me for a job. Wow.
Close your eyes.
Abrazo.
Your eyes are open.
Abrazo.
Oh, yeah.
Oh, you know, yes, I received an email last week. That I did.
Granted to the as far as like.
Because I learned I'm teaching like things.
Yeah.
Exactly, that's what.
So I.
And it's not gonna be as
I
tiring.
just recommend which is like the second
You really want to do that? Of course. Oh my God, there's this one. Yes, I hate it. I hate that. I hate that. You know, if I poke you and I don't complain, I really.
You gonna do the buttons?
Ah,
Combination.
I
I
am.
was thinking, and I said, and he that's good, so I don't know.
How do you find that? It's like, oh. Well, you have to. Well, yeah, you have to use a tourniquet. But anyways, sometimes you have to take blood. So like right here.
It's the bouncy one.
Yeah, like the bouncy thing. You
Oh, I feel it.
there, and then you know, like you have to know what direction is going. So it's going like this. So that's where you I have a start. Look here. It goes right here. The lady put it right here. Right here. Ooh,
I love the car.
It's.
This is
I've had it before, and it's not necessarily bad, it's just, personally, I mean, I think, either PT or massage, you know.
Yeah, hey, go for it. We'll talk more after class.
Yeah, for sure.
Okay, folks, let's come back together. We're gonna now move forward and try to do these problems on our own. Everybody ready?
Yes.
All right. So turn to this page where it says 3.2. And what we're going to do now, we've seen a lot of big picture, like how to extract information from either form. So you can extract the information from factored form. You can extract the information from expanded form. Extracting information from factored form is easy because if it's already factored, you know the x-intercepts, and you can do the lazy person FOIL, and you get the y-intercept, the end behavior. So factored form is easy. The real work that we're about to do is taking an expanded form polynomial and factoring it. So really that is all the work of the rest of the chapter, is how do you take an expanded polynomial and factor it. Because, and again, for instance, like looking at number 1 here, this is an expanded polynomial, so I immediately know the end behavior. What's the end behavior? It's like that, right? What's my y-intercept? -1. So what I don't know now is the x-intercepts. And in fact, just looking at this, it's not factorable. So, well, okay, I don't know if it's factorable or not yet. But this is what we need to figure out is how do we take an expanded polynomial and factor it? So let me just suggest that here so you can see what the goal would be. This is what your end goal would be. Let's say that I have a really long polynomial, well, not really long, but we'll just say x to the 4th minus 7x cubed plus 8x squared minus 9x plus 12. Now, this is just a make-believe example, okay? So just work with me on this. What we're going to see how to do is using synthetic division to factor a polynomial one factor at a time. So I would take this polynomial, I would do synthetic division, and that would give me one factor, one x-intercept. And then the rest would be a polynomial reduced by 1 degree, maybe x cubed minus 6x squared plus 8x minus 9. So that's just the result of one application of synthetic division. Then I want to keep factoring this. So I would get to keep this x minus 3, and then I would do synthetic division on this, and that would give me another factor, maybe x plus 5. And then this cubic would reduce by 1 degree to something like x squared plus 7x plus 12. Then I would keep doing synthetic division to keep bringing this down. Although at this point, since it's quadratic, we can just factor this. Like once you get to a quadratic, you can stop all the synthetic division business and just factor it. So at this point, then, I would know that I have x minus 3, and then x plus 5, and then this I can factor. What multiplies to make 12 to S make 7? 4 and 3. And then we'd be done. So I want you to see that from a bird's eye view, that that's what we're ultimately trying to do, is go from expanded form which has limited information. All I know from expanded form is end behavior and y-intercept. That's not enough. So we use synthetic division to factor, factor, factor all the way down to factors, because now I have x-intercept information. And now I can actually draw a good graph. So the question remains then, how does synthetic division allow us to do this one step at a time? So taking a look here, we're going to start off slow. We're going to start off easy with taking just quadratics and factoring them using synthetic division as opposed to factoring in quadratic formula. I feel like I should have more markers. Oh, there's one, there's one. All right, now I have more. So we're going to take a look at number one. I believe we already did something like this in our notes, so this will just be a quick review. What we're looking at in this problem is we're saying, is 4x squared plus 3x minus 1 divisible by x minus 3? So is it divisible by x minus 3? That'd be like saying, is 20 divisible by 4? It is, and I know it is because I can rewrite it as 4 times 5. Right? If I said, is 20 divisible by 3? No. I could get really close. I could say 3 times 6 is 18, and then add a 2 on. Right? That's not really what we're wanting. We're wanting something that's evenly divisible with no plus anything on the outside. But if we did do this, it's at least something. I took the number 20, I rewrote it as a product, and added and as an addition. But what I really want is to take something and just rewrite it as a product with nothing outside, plus 0. So what we're saying then in this problem, everyone write this down in your own handwriting. We're saying, as a question, can we take 4x squared plus 3x minus 1 and rewrite it as x minus 3 times something? That's a question. What?
So let's find out.
Yeah, let's find out. So that's a question right there. We're saying, can 4x squared plus 3x minus 1 be rewritten as x minus 3 times another factor? And so let's follow the logic on this. If x minus 3 were a factor, what factor?
So you follow logic on this. So following logic, and your equals to sign should be 2x. Isn't it?
What do you mean for what's in here?
No, for both of them. So 2x times
not necessarily.
2x would be 2x squared. I mean 4x squared.
Right, but it could also be 4x right here. Because then x times 4x would be 4x squared. So yeah, you could try to figure out what that is by playing around. By all means, you could.
Well, you have 2 options. We already have 2 of the options.
Yes, yes we do. Although to be fair, it's worse than that. Because it could actually be 1/2 x and 8x.
That's all.
So how many options are there?
It's 3.
Infinity. So we want to not play around to find the answer because there are infinitely many options. And instead we're going to see how this technique works. But you're right, you could try to guess it. Okay, so if x minus 3 were a factor, what does that tell us about our graph?
That one of the x-intercepts.
Right. So everybody draw a little graph. If this were true, okay, because right now we're just asking the question. We don't know if it's true or not. But if it were true, then x minus 3 would be a factor, which means 3 is an x-intercept, which means the coordinate 3, 0 is on the graph, which means if you input 3, you should output 0. So now that's our experiment. We're going to do synthetic division with 3, and using those coefficients, 4, 3, -1. We're going to check to see if it's true. Does it output a 0? This is an experiment we're doing. We're going to go back. Yeah, I want us to see. Thank you. Yes, absolutely. It does say long division. I will go back to that. For right now, let's see how this works using synthetic division. Thank you, Nadine. Seriously, truly. Thank you for pointing that out. I will get back to that. And I'm sorry, I'm doing something completely different from the instructions, and I'm probably confusing. Okay, so let's try it. We drop the 4. 4 times 3 is 12. So multiply, add, multiply, add, and I got a 44. So is 3 an x-intercept? No, it is not. What we know for sure is that we have the coordinate 3, 44. So way up here on my graph is the coordinate 3, 44. So the original thought that there was an x-intercept right there is incorrect. There is no x-intercept at 3. The coordinate's way up there, 3, 44. However, this still gives us really good information. So here's what we end up with. The last term is the remainder. That will become its own term. Everything in front of the remainder will become a polynomial. And this will also become something. So we have 3 drop-down arrows that are all going to tell us information. The first chunk is that 3 was representing the factor x minus 3. So there's one of our factors. So x minus 3. The second chunk, since we started at x squared, we reduced that by 1 power, or by 1 degree. So now that's going to be x, no x. So now that's our next factor, 4x plus 15. And then we just drop down to 44 as a remainder. That's what synthetic division just told us, is that yes, indeed, 4x squared plus 3x minus 1 can be rewritten as this. Now, to be fair, this is useless to us, because we don't want a plus 44, we want a plus 0. Because in order to use the zero product rule, we need something times something, not something times something plus something. That ruins everything. But it's still true. Okay, this is still true, that 4x squared plus 3x minus 1 is equal to this. And it wouldn't hurt just to verify that for ourselves. What is x minus 3 times 4x plus 15 plus 44? I want to find out. Just to be sure, FOIL, 4x squared plus 15x minus 12x minus 45 plus 44. Combining like terms in the middle, that's 4x squared plus 3x. Combining those like terms, minus 1. Is it 4x squared plus 3x minus 1? Was that the original problem?
Yes.
Yeah. Okay. So synthetic division provides a technique to rewrite a polynomial as something times something plus something. That's what synthetic division does. It's a technique for rewriting an addition problem as something times something plus something. Obviously, our goal is that that plus something is a 0, because then it would be genuinely factored. Okay. Now, that's one way this technique works, and that's how I started off saying, is that how do we read synthetic division? We read the information right off the bottom. We drop down those 3 arrows, and we rewrite the original polynomial like we just did. So here's the key takeaways I want you to write down. And by the way, I wrote skip number 2, so you have more room to write all this stuff down. So the first thing we can say is that, let's just say method number 1. Is that we can say the polynomial 4x squared plus 3x minus 1 is in fact equal to x minus 3 times 4x plus 15 plus 44. So in answer to our first question, is 4x squared plus 3x minus 1 divisible by x minus 3? No. It's not evenly divisible. It's not cleanly divisible. So that answer is no. However, to do the problem that was actually given to us, because I realize I'm reading that problem rather uniquely, I'm saying the problem says, is it divisible? Technically, what they want us to do is actually divide it. They want us to actually divide it. So here's the actual problem they gave us. Number 1, the problem is 4x squared plus 3x minus 1 over x minus 3. That's the actual problem they gave us. I chose to interpret it as a question about divisibility, because I believe it helps us to better interpret the information that we get from synthetic division. But that's the actual question in number 1. So how do we do this problem?
FOIL the top one, and then we can, if there's any similar, or like there's one on top, like negative, negative x, like x negative 3, and possibly multiply.
Right. And by FOIL, you mean factor. We can factor the numerator using the information we just got. So in fact, we can take that numerator, rewrite it as x minus 3, 4x plus 15, plus 44. So everyone go ahead and do that. What we're doing right now is we're rewriting the numerator using the information that we got from synthetic division.
Take that out, and your answer is 4x plus 15, with the remainder 44.
With the remainder 44. So now, Hector, you're really close. Okay, there's one more thing we have to do here. We cannot cross out the x minus 3 yet. You're only allowed to cross things out if everything is multiplication. And everything is non-multiplication. We have a plus sign right there. So you cannot cross those out. However, whenever you have a fraction that has a plus in the numerator, you can split it into 2 different fractions. So everyone just, make sure you agree with me here. If I said 1/5 plus 3/5, do you all agree that that's 4/5? And if I say that's really 3 plus 1/5, then I rewrite that as 3/5 plus 1/5. Right, so anytime you have a fraction with a plus, you can split it into 2 fractions. So I can take this one fraction, which is 3 plus 1 over 5, and rewrite it as 3 over 5 plus 1 over 5. That's what we're about to do here. We have a plus sign. So now I'm going to go ahead and rewrite that. And what I have now is one fraction plus another fraction. They're both going to be over x minus 3. Because I'm just rewriting it as two fractions. The first one will be x minus 3, 4x plus 15. And the second one will be 44. Now we can do what Hector wanted to do, which is cancel out the x minus 3. Also, we now have a really clean answer. The answer is simply 4x plus 15. That's not a fraction. That's just a regular polynomial there. Plus the fraction, 44x minus 3rds. Don't know how to pronounce that. X minus 3rds. It's 44x minus 3rds.
The first one to pronounce it correctly.
Yeah, I don't know if that's correctly, but that's the answer. So, to the original problem, I'm going to write it down one more time so you see it really nice and big. 4x squared plus 3x minus 1 divided by x minus 3 is equal to 4x plus 15 plus 44x minus 3rds. And remember that, because we're about to see a totally different technique to get us to the same answer. The long division technique. Because to be fair, this problem said use polynomial long division.
Oh.
Now, even though I'm about to show you long division, and I want you to do it with me right now, we're only going to do one, and it won't be on the test. So, what I want you to do right now is just experience it with me. Write it down. Experience it. You know, let go of any hesitancy that you might have about it. Just do it. And then just know that it's just another technique that exists out there. We're not going to focus on it in this class, but I want you to see it because it's kind of cool. Okay, now, first of all, what does the phrase long division make you think of?
Like the sign for square rooting and then go there.
Yeah. Well, it's not quite the sign for square root, but yeah, long division, right? So let's do an example of long division. Let's do 8 goes into 30. Okay, that's like a basic division problem. Now, when's the last time you did division by hand? 5th grade? Because these days you have to divide.
Monday?
Yeah. Oh, Monday you did? Okay, well, good. I mean, maybe you do it, maybe you don't. I mean, I long divide on paper all the time if I'm just working in a calculator. But for the most part, people use calculators for this. In any case, it goes all the way back to your childhood. How do we divide 8 into 30? First, we say, does 8 go to 3? Does 8 go to 30? Yeah. So you write 4. You write 4 because what you're going to do now is multiply. So 4 times 8 is, oh, that's too big. It's not 4. Teasing. How many times does 8 go to 30? 3 times. Okay, now you multiply 3 times 8 is 24. And then what do I do? Subtract. And that's a 6. And now what?
The remainder is 6.
Yeah, right now you could stop. Well, let's keep going. Put a decimal. Put another 0. Stop the 0. How many times is 8 going to 60?
No.
The 7? 8 times 7 is 56?
Yeah.
So 56. What do we do now? Subtract. That's a 4. Stop another 0. 40. How many times is 8 going to 40? 1. Wow. Okay, so does everyone agree that the answer is 3.75? Because then I put 40 and I subtract it 0. Okay, 3/4? Yes, 3 3/4. Yeah. Now hold on to that. 3.75, and Hector just said 3 3/4. Everybody watch now. We're getting all that decimal business. Something very important to look at right here. And that is, had we just stopped then, or we just stopped right here, you can read the answer by going around clockwise in a circle, and you'd say the answer is 3 6/8. Have you ever seen that?
Oh yeah, then you would just like simplify it from there.
So the answer is 3 6/8, and so that's really 3 3/4, which is 3.75. Okay, so that's long division, and this whole circular loop thing here is pretty important. That's how you read the answer. Okay, so now that we've all revisited 5th grade, let's talk about doing this problem. Now this is what I want you all to write down. Write this down with me. We're going to divide 4x squared plus 3x minus 1. We're going to divide it by x minus 3. Now that right there might be enough to put you in trouble. Right? Like, oh, what? how do you begin this process? I mean, 8 to 30, we can ask simple questions like how many times is 8 going to 30? But how do you even ask how many times is x minus 3 going to 4x squared? Let alone plus 3x minus 1. Right, so it's one at a time. It is absolutely one at a time. And what we're actually going to look at is what do you have to multiply by the first term to get the first term? So what do you have to multiply by x to get 4x squared? 4x. So you write 4x right above it, everybody. And just as before, when we put the 3 up there, we then immediately multiplied 3 times 8, and we wrote it down below. So now we're going to multiply 4x times that whole thing. So 4x times x is 4x squared, and then 4x times negative 3 is minus 12x. Now what do? Subtract, just like we were doing. So, but subtraction of a polynomial, it's a lot easier to remember. If you're going to subtract a polynomial, what do you really do? You change all the signs and you add. So let's change all the signs. That becomes a minus, that becomes a plus. Now you can add. The first term will always cancel out. It hit better. Otherwise, you chose the wrong number. So that cancels out, and now we have 15x. And then what do? Yep, we drop the next term. So now we have 15x minus 1. We have completed one chunk of long division, and now we just start again. So now we say, what do you multiply by x to get 15x? 15. So that'll be our next number, 15. So now we're going to multiply 15 times x minus 3. So 15 times x is 15x. And then 15 times negative 3 is minus 45. So what do? We subtract, which means you change the signs. I could just had a moment of extreme joy. And those cancel out. And now adding together, negative 1 plus 45 is 44. It is very exciting. I admit that. So now, reading it in a clockwise formation, just like that was 3 and 6/8, in other words, whole number, 3 and numerator over denominator, 4x plus 15, and numerator over denominator. So the answer is 4x plus 15 plus 44x minus 6.
Because in terms of writing this, that was way less. You would need to write way less than that. You know, you'd write way less than on
Right, yeah. Like you're saying this was faster?
Yes.
Yeah, see, I mean, after introducing synthetic division, you could probably sell somebody on long division. But like, yeah, forget all that, I want to do long division. Whereas if I just walked up to you and said, hey, you want to try long division? Most people say no. But in a contrast, yeah, you might be like, wow, long division, that's pretty cool, because it's the exact same answer. So when you see this problem, and it said use polynomial long division, you could have just done long division. But we're not building on the skill of long division. We're building on the skill of synthetic division. Synthetic division will allow us to do more. Lee.
What I have found at the Learning Center is with these two different ways going about the situation,
Yeah.
people are split on which way they enjoy doing.
Yeah, oh, I'm sure that there's a split.
Is there a war in the Learning Center about this?
Yeah.
No, there's not really a war. But when it comes down to people asking for instruction on how to accomplish this,
yeah,
one tutor will show them one way, another tutor will show them their way, and you get to the exact same answer, but you have to explain like what is really going on.
Yeah, yeah.
But everyone likes their own way.
Exactly right. Everybody prefer, and it's good to know both, honestly, because then depending on what you're trying to accomplish, you can do either one. And in fact, it is context specific. This next problem, which we're not going to do, you're dividing by x squared plus 4. The only way to do this problem is long division. You cannot actually apply synthetic division to this problem. That's partial lie. You could, but not with x squared plus 4. Remember, we only deal with x minus 4, or x plus 4, not x squared plus 4, x squared minus 4. Okay, so folks, that was it. We now see that when you do division, you could do long division, which we're not going to keep doing. Or what you do is you use synthetic division to rewrite the given polynomial, and then you could go ahead and divide it by the other factor and reduce it down. We're not overly interested in actually doing the division. What we're really interested in doing is just rewriting a polynomial as a partial factor with a plus at the end. That's what we're really interested in doing is method one. Okay. Other questions before we keep going? Okay, so now moving forward, you'll see it says use synthetic division, write the polynomial in the form p of x equals d of x times q of x plus r of x. And so, just to be clear again, when you rewrite a polynomial using synthetic division, this is the divisor times the quotient plus the remainder. So divisor, we'll write it again on this next one. Quotient, remainder. I'll leave that up as this. All right, ready to try the next one? Two people are out of the room, which is a significant percentage of this class. But then again, I suppose we should just be going. People have to class. Okay, number 5. Everybody, let's take a look at number 5. Let's again interpret the problem. We're going to follow the logic. It's saying, is 3x squared minus 2x plus 1 divisible by x minus 1? Now what that means is we're asking a question, we're doing an experiment, we're saying, can 3x squared minus 2x plus 1 be rewritten as x minus 1 times something?
Not a function of the variables, like e x equals 2x.
Yeah, that's the form that our answer should be when we're done. So we're using method 1. We're not doing method 2, we're doing method 1. Okay, so again, to understand where we're going with this, we're saying, if you could do this, x minus 1 would be the factor, which means 1 would be an x-intercept, which means the coordinate 1, 0 is on the graph, which means input 1, output 0. We're inputting the number 1 into synthetic division. Now see, I show you all that in chain of reasoning because the alternative is to say, whatever you see, divide by x minus 1, change the sign and use the number 1. Well, I mean, that's just like some sort of thing you're memorizing, right? I don't want to just say, well, whatever you see in the divide by, they change the sign and put that number there. I want you to know why we're using that number. So that's the chain of reasoning that gets you here. Now we do the synthetic division, drop of 3, multiply, add, and no, it's not an x-intercept. However, we still know something. We know input, output. We know that the coordinate 1, 2 is on the graph. So the coordinate is actually there. That's what the coordinate actually is. And we do know that we can rewrite this polynomial now, that we get 3 chunks of information out. We've got the one that we plugged in, which represented the x-intercept, which represents the factor x minus 1. The next chunk of information, which since we started at x squared, we reduced by 1, and now it's x no x. And so that's 3x plus 1. And then the remainder is plus 2. And so the problem said, rewrite the polynomial in the form. And so we're going to go ahead and rewrite that. We're going to say my function f of x is 3x squared minus 2x plus 1, which I can rewrite as x minus 1 times 3x plus 1 plus 2, which I will then label. This is my divisor, this is my quotient, and this is my remainder. Now, right there, just doing that, okay? Just that one line of work. We use synthetic division to get us there. Just that, again, is pretty worthless. Because doing that didn't help us find any x-intercepts at all. Do we know any x-intercepts yet? Nothing. Okay? This is worthless to us, but that's how you write it. Okay? That's just how you get the information out of synthetic division. What do we really want? What do we really want? We want to choose a number to plug in so that we get a output of 2. 0. 0. That's what we really want. Because if that were a 0, would it be factored? Yeah. So that's what we really want. This whole technique is here such that if we chose the right number, if we just chose the right number to input, we would get a 0, and then there would be nothing there, and we would successfully factor the polynomial, which is our whole goal. So really the name of the game is choose the right number so that your output is a 0. Because then you took your polynomial and you factored it. How does everybody feel about that? That's what we're doing. Okay. So that was number 5. Let's all try number 6. Do that whole process for number 6. So number 6, I'd like to see you all kind of show your chain of reasoning, just like we had been doing. You would say to yourself, can 4x squared minus 5x plus 3 be rewritten as x plus 3 times something? Because if you could, then you know that the x-intercept would be. Yeah, that'd be nice.
So,
And if -3 was an x-intercept, you know that you got the coordinate -3, 0, which means if you input a -3.
sound like the state of national, or was the declaring a national emergency.
Oh yeah, I sound like that.
I have a quick question.
Yeah.
So I was able to catch.
Yeah.
Almost on that. So drop the 3.
Yeah, so you drop the first number, then it's always multiply by this number. So multiply, put the next number there,
Okay.
and then add.
And then have those.
And then multiply,
Oh, okay.
and then put it there, and then add. So it's always multiply, add, multiply, add. Let's do this one together. Drop the 4. Now multiply,
Well, the next one right here, you can add.
and then add. Yep. Now multiply again, and then add. There you go. That's enough. There you go. Lovely work. That looks wonderful. For the next one. Hey, that's good. You always reduce by a single x power. So since you started at x squared, that's going to be the x no x. That's not an x. That's your remainder. So yeah, since that you started at x squared, you then reduce that by x. And I'll put it in there for parentheses around it. Does that answer your question?
Yeah.
Okay. Yeah. You're always reducing the polynomial. Okay. Okay, when you drop the 4, and then that's a -12. Is that a -5? Oh, yeah, that is a -5. And then, is that a negative? Oh, yeah, keep going. Did we just do that wrong? That was a negative. Yep. Oops, so everything happened. Sorry. Okay, so you bring down the coefficients 4, -5, and 3. You drop the 4. Now that's 4, so times -3 is -12. Add them together, get -17. Multiply the -3, that's +51. And then add them together, and you get 54. Now to Emily's question, you're going to have 3 arrows coming down. This whole chunk right here, I would go ahead and put the variables in there right now. You started as an x squared, so now it reduces to x no x. And so then your first part, -3, that's the x plus 3. And then the next chunk is 4x minus 17. And then the last bit is just the remainder. Emily, does that answer your question?
Yeah.
Okay. Now, Emily, I like your question though. How do you know for sure that it shouldn't be x plus 3 times 4x squared minus 17x? Why would that be wrong? What would happen if I foiled that? You get 4x cubed. And that's not what we started with. That's why you always have to reduce the exponent by 1. Okay, so is that what everybody finished with? Okay, well, that's it. That's the end of the problem. We just rewrote it as the divisor times the quotient plus the remainder. And our goal is to find the correct input number so that the remainder is 0. That's what we're going to work on. Now, in number 8, you might notice in number 8 that it looks scary. Why does 8 look a little scary? Yeah, because it's fraction, and we start at a cubic, which is slightly longer. So, but let's try it again. Here's our experiment. We're saying, can 2x cubed plus 1x squared plus 2x plus 1 be rewritten as x plus a half times something? And if that were possible, we would have an x-intercept at -1/2, which means that it'd be a coordinate at -1/2, 0, which means if I plug in -1/2, I should get an output of 0. So my coefficients are 2, 1, 2, 1, and away we go. So all of this multiplying by a fraction, I'm not too interested in us doing lots of problems with fractions, because I want to make sure we know the concept and not all this arithmetic fractions. But you'll notice you're just doing half, right? Everybody can do half in their head. So drop the 2. So 2 times a half is 1, but make it negative. And then 1 and -1 is 0. Half of 0 is nothing, make it negative, that's 0. Add them together, 2 and 0 is 2. Half of 2 is 1, but negative, so it's negative 1. And 1 plus 1. 1 plus negative 1 is 0. Ooh la la. 0, that's very exciting. Remember, that's our goal. We want a 0. So now, how do those 3 arrows drop down again? And notice, we started as an x cubed. So what am I going to write down? X squared, x, no x. So what I really have here is the first factor is x plus a half. Then I have 2x squared plus 0x plus 2. Then I have a plus 0 again. Okay, well, more can be done with this polynomial. For instance, you could just write x plus a half. And then I don't have to write plus 0x. I can just write 2x squared plus 2. And I don't have to write plus 0. So in fact, did I factor this polynomial? Yeah. Well, remember, we were asking the question, is x plus half a factor here? And if negative a half is the x-intercept, the factor is always you change the sign. Yeah. Okay, so we did in fact factor it because there was no remainder. So yes, 2x cubed plus 1x squared plus 2x plus 1 is actually factorable. Which, that's something we couldn't have done without synthetic division. Plus, what can I take out of this one? I can take out 2. So now I can rewrite that as 2 times x plus a half times x squared plus 1. And that's basically as factored as this one is going to get. The x squared plus 1 doesn't further factor. It's not factorable because it is a parabola that doesn't touch the x-axis. There are no x-intercepts, and therefore it is not factorable. Okay. We're really building steam now, folks. And I'm not saying you're full of hot air. I'm saying we're building good momentum. So, we have this technique called synthetic division. And it allows us to rewrite a purely expanded form polynomial as a partial factoring. And I call it partial factoring because there could be a plus number at the end. So if there's a plus number at the end, it's worthless to us. But if the plus number at the end is a 0, then we really did factor it. And then you keep going and you try to keep factoring. So in these next couple problems, it's just introducing us to some more terminology. So let's just acquaint ourselves with the terminology.
You put an absolute value?
What?
I'm writing down the notes. I'm writing down to that part.
Oh yeah, that's a 1. Yeah, that's a coefficient. Because I brought the 2 out of here, and I brought it all the way up front. Well, this one nothing comes out of it. But this one, like, had I.
Well, let's just say if it did have, if it did have a, what is it called?
Yeah, here, everybody, let's take a look at this. What if I had 3x plus 6 and 5x minus 1? Okay, so from here, can I take out a 3? And from here, can I take out a 5?
Yes.
Okay, so I can do that separately, and I can do this as 3 times x plus 2 times 5 times x minus 4. But I'm not going to leave the 5 there. I want to bring it up front. So it'd be 3 times 5 times x plus 2 times x minus 4. And then I combine the 5 and 3 together to be 50 x plus 2, x minus 4. So that's all I did here is I had the 2 that I could take out of there. And instead of leaving it right there in between the 2, I brought it all the way up front. Nadine, does that answer your question?
Yeah.
Okay. Yeah, thank you for calling attention to that. I didn't explain that, I just did it. Okay, really good questions, folks. You all are asking really wonderful questions. So, we're going to introduce 2, just so we all know what the remainder theorem states and the factor theorem states. The good news is you already know how to use both. Because we've already been doing it, and now we're just going to attach the word to it. So, let's all look at number, let's look at number 2. So let's look at number 2. What we have there is 8x equals 8x cubed plus 12x squared. Okay, now parentheses. 12x squared plus 6x plus 1. So look at what they're asking us to do. It says determine P of C So first of all, what C value did they give us? Yeah, -1/2. Now keep in mind, if I actually wanted to find P of C, that would mean I'd have to plug, what's C again? -1/2. So I'd have to plug -1/2 in there. I just want to remind everyone that no one wants to do that. Imagine if I plugged in -1/2 of this. I'd have to do 8 times -1/2 cubed plus 12 times -1/2 squared plus 6 times -1/2 plus 1. Nobody wants to do that. Because now what do I have? I have 8 times -8 plus 12 times a positive 4, and then, well, 6 times -1/2, I'll just call that minus 3 plus 1. And then I got to come back here and I'm going to call 8 times an 8 is -1, and then 12 divided by 4 is 3, and then minus 3 is 1. And now my 1's cancel out and my 3's cancel out, and voila! P of -1/2 is 0. Now, who enjoyed that process? We enjoyed it a little bit. I enjoyed it a little bit. No, but nobody does. So nobody wants to do it that way. So instead, what the remainder theorem states is that instead of plugging a number into the actual function and actually calculating it, the remainder theorem states you can just do synthetic division. So let's jot that down. The remainder theorem states that the output of synthetic division, synth div, is the output of the function. Right, so that's wonderful, that's handy. Instead of actually plugging numbers into functions, you can just do synthetic division and that gives you the output. That's all the remainder theorem states. So now, instead of actually plugging -1/2 into the polynomial, I can just do synthetic division with -1/2. And this part we'll actually all write down here. So that's going to be 8, 12, 6, and 1. By the way, you always want to double check x to the 3, x to the 2, x to the 1, no x. You want to make sure all the terms are there and present in the count. Okay, so now synthetic division. Notice how much easier this is. Drop the 8. Half of 8 is 4, make it negative. Add 8. Half of 8 is 4, make it negative. Add. Half of 2 is 1, make it negative. Add. 0. Does anyone think that was easier than plugging -1/2 into the function? That's the remainder theorem. The remainder theorem just states that doing synthetic division, the output is the same output you would get if you actually plugged it into the. Yes?
And for that one, you wouldn't use the sign.
Well,
You know how
correct. They actually literally told us a number to plug into the function. And
it's negative.
right, yeah. You don't change it because if I'm plugging -1/2 into the function or I'm plugging -1/2 into here, it's the same number. But now we can look at this and we have all the information to drop our 3 arrows down and interpret what we just got. So first of all, we started at x cubed, so that'll reduce to x squared x no x. So that's part of it. Now the -1/2, we change the sign. Because if the actual x-intercept is -1/2, the factor is x plus 1/2. And now the x squared, 8x squared plus 8x plus 2, and the remainder is 0. Now there's really not a point in writing plus 0. Because it might make you think something fancy is happening that isn't. The point is we factored it. We took that polynomial and we factored it. And that's what the factor theorem states. That the real number c is a 0 of p if only if x minus c is a factor of px, or p of x. So we're just stating that if the number you plugged in caused a 0 to come out, then you put the opposite sign into a factor, and that's one of the factors. Yeah.
Did you skip over number 1 for this?
Hey.
So,
Yeah, we can just totally cross it out. That's fine.
So for this one, you don't have to use sign.
What we just did.
No, for the negative.
Yeah, correct. Because they actually told us a number to plug in. Because look again, they said determine P of C. That means plug C into the function. What's C? -1/2. That means we actually plugged -1/2 into the function. So we actually plugged -1/2 into the function, which is the same as actually plugging -1/2 into synthetic division. Because remember, synthetic division is the same computation as plugging it in there. So yeah, whether you plug in -1/2 into the function or you plug in -1/2 into the actual synthetic division, there the sign doesn't change. I'm glad you guys are asking because let's be very painfully clear about it. The only time you change the sign is between factor and x-intercept. So when we say the x-intercept is -1/2, the factor is x plus 1/2. It's only the switching between the factor and the x-intercept. Like maybe it'd be helpful if everybody drew a little thing here and kind of reminded ourselves if the x-intercept is -1/2, the factor is x plus 1/2. That's the only time you change the sign is between the actual x-intercept and the actual factor. More importantly, I hope that you can all connect the dots as to why that is. Because if you use the zero product rule and the factor is x plus 1/2 times a bunch of things equaling 0, then you set that equal to 0. And what happens if you set x plus 1/2 equal to 0? When you solve for x, what happens? It moves the 1/2 to the other side and it becomes -1/2. So as we sit here and memorize times that we change the signs, that sounds like magic. Hey, wait, is this one of them times we change the sign? We're not ever changing a sign like out of magic. We're doing algebra. We're just skipping all the algebra and getting to the result. So in fact, in mathematics, we never change a sign. There is no magic where you take a number and you just change the sign for no good reason. There's a reason. We're just skipping all the way past the details and getting to the end. So when we say the factor is x plus 1/2, you should be literally thinking, okay, I'm going to set that equal to 0. I'm going to subtract 1/2 from both sides. Oh, the x-intercept is -1/2. Oh, that's why it's -1/2. So no, nobody changed any signs. I'm trying to be funny, but also forceful. Okay, I hope that makes sense. Nobody's changing any signs. Okay. Well, that's it. That was number 2. The question was, determine P of C. P of C was 0. So if you wanted to be very clear, P of -1/2 is 0. That was the first answer. And then it said, if P of C is equal to 0, which it is, then factor it, which we did. I'm trying to think of a time when you would change a sign. You walk up to someone who's cheating off you? Yeah.
I know you didn't ask me, but that would be a good one example.
Sure. I don't know what that means exactly, but yeah.
Like,
I don't know if you're talking about the relationship or you're talking about
if someone is cheating off you, you change the sign, so they get it wrong.
Oh, I see what you're saying. Yeah, because there was.
Okay. I thought you meant like in a relationship.
That's why I was writing.
So it is a relationship, but it's not a bad, it's not a good one.
Yeah.
But there was I do know that when I was taking class, one of the students they talked about how they knew that someone was cheating off them. So they would go through with all their signs, and at the very end they would erase what they had.
Wow, geez, or just sit somewhere else.
Yes, you can't get up and sit somewhere else.
Of course
during
you
a
can.
test.
Of course you can. You just go up to the teacher and say, I'm going to sit in the back. Of course you can. Okay, so let's keep going. We all skipped number 1.
And you're the first person I've heard.
Say that?
You're the first person.
Sit anywhere you like.
During a test.
During a test.
You
Okay,
gotta be doing-
I mean, you just can't say that. I have 1 person for taking it. So
That's true.
nobody's cheating. Okay, you are given a polynomial and one of its zeros. So now let's see what's happening. So we understand the remainder theorem just states that synthetic division gives you the same output as if you plugged it into the function. And the factor theorem tells you that if you do get a 0, you just successfully factored your polynomial. That's all those things mean. Okay, so now, what we're about to do now is start baby stepping our way to a full solution. So we're going to take a look at number 5. And we have written down here f of x equals x cubed minus 6x squared plus 11x minus 6. And it says you are given a polynomial. There it is. Remember our end goal. What's our end goal? I want to rewrite it as a factor times a factor times a factor. That's our end goal for the whole chapter. Is how do I take an expanded polynomial and rewrite it as a factor polynomial? Why? Well, remember, in the expanded polynomial, all I know so far is the end behavior and the y-intercept. That's not enough information. I factor it so I can get the x-intercept. Okay, so that's a big picture of what we're trying to do. So it says you're given a polynomial, and they gave us one of the zeros. They're actually telling us that c equals 1 is an x-intercept. Why they call it c instead of x-intercept, I don't know. But they're telling us that one of the x-intercepts is 1. This is wonderful. That means I can go ahead and start drawing my graph now. I have an x-intercept at 1. I absolutely know for sure. This is not a guess. This is not an experiment. They're telling us one of the x-intercepts is 1. Now it says, find all the rest. Back to the polynomial. That's what they gave us. This is our goal. We're about to do it using synthetic division. Ultimately, this problem is really, really easy, but it's nice to see the whole process. All right, so we know that if we plug in a 1, we should get out 0, because the coordinate 1, 0 is on the graph.
We know that our y.
Yeah, we know our y-intercept is negative 6, and we know our end behavior looks like that. Okay, so we're going to plug in 1 and see if we get a 0. We got it, because they're telling us we're low. So our coefficients are 1, negative 6, and y, negative 6. We're going to plug in 1. And we'll do synthetic division. So we put 1, multiply, add, multiply, add. Did everyone get a 0? Now this is really exciting. Again, I always wrap this first chunk in parentheses, and then I have my 3 arrows, so that's part of it, that's part of it, and the last part of it. So now what do we have? We do know now that since 1 is an x-intercept, we're going to change the sign and make that an x minus 1. We started at x cubed, so now we're going to make this x squared x LX. So now we have x squared minus 5x plus 6. And the plus 0, I'm not even going to bother writing down. Now, all of you, I bet, are already tempted to just factor this, because you can all do it. How do you factor this? What multiplies to make 6 that adds to make negative 5?
Negative 5. Wait, no, like negative 5. No, it's not right.
You are correct that it is not right. It always helps to make a factor table. 6 is either 1 times 6 or 2 times 3. We want to multiply to make a positive, which means plus times plus or minus times minus. We want it to add to make a negative, so it must be minus times minus. And so is it negative 1, negative 6, or negative 2, negative 3? Negative 2, negative 3. So x minus 2, x minus 3. You'll notice that right here, we did not change the sign for those numbers. Right? Okay, we did it. That's it. We're done. We factored it. We reached our goal. That function is actually x minus 1, x minus 2, x minus 3. That right there is the whole purpose of the chapter, is to take a fully expanded polynomial and change it into a fully factored polynomial. You'll notice to do that, we did 1 synthetic division, we did 1 factor, a traditional factor of a quadratic. Now we can go back to our drawing. And everybody, let's make a good drawing. Don't make a bad drawing, a good drawing. So we know we have our end behavior, which I don't have a good spot to put it, but our end behavior is cubic, like that. And we know our y-intercept is at negative 6. We know our x-intercepts are at 1, 2, and 3. I just change the signs. So now that's a 1, that's a 2, that's a 3. And now we need to insert our end behavior. So our end behavior, we have a tail going up to the right. So from the farthest right-hand x-intercept, we put our tail going right. Our tail goes down and to the left. So from the farthest left x-intercept, we put the tail going down. And from those tails alone now, we should be able to finish the drawing. So definitely this tail is going to proceed through that y-intercept. And then otherwise, each of these exponents were a 1, 1, 1, which makes it a slice, slice, slice. For all slices, this just means you go slice, slice, slice. Just imagine, right here, number 5. Right there, just right there. That's one problem. That's the amount of work you'd show, no more, no less. That's an incredibly rich body of information and knowledge right there. I mean, that takes somebody with an incredible amount of knowledge of mathematics to follow that and understand that and then do it. And so I'm complimenting all of you. Like, to do this process, this is not something you just scribble down with a couple steps, or like skip your steps, or like don't write anything down. Like, there's a lot going on here. This is a very complex problem. Who has questions? Oh, my phone went off, didn't it? Is class almost over? No, my phone didn't go off. Okay, good. All right, yes. You did not what? Have a question? Oh, okay, great. All right, well, we did it, folks. That's an example of doing the whole problem. Let's all do number 6, and that's probably about all the time we have. So in number 6, once again, they're telling us, here's a polynomial, here's an x-intercept. So the polynomial starts as x cubed plus 2x squared minus 3x minus 6. And they're telling us that negative 2 is an x-intercept. So if negative 2 is an x-intercept, do I put it at negative 2 or positive 2?
Negative 2.
Negative 2 is the x-intercept, so that is actually the dot. My coordinate, is it negative 2, 0 or 2, 0? Negative 2, 0. Like, no signs have been changed at this point, right? They're literally telling us that's the x-intercept, that's the coordinate. What number do I put in synthetic division? Negative 2, because that's the number I'm actually putting in. So now we do synthetic division, 1, 2, negative 3, negative 6. So we do synthetic division, 1, multiply, add, multiply, add, multiply, add. Now we read the information from our synthetic division. So again, we have 3 drop-down arrows of information. Again, we started as a cubic. So now we reduce to x squared x no x. Now, wink, wink. How do I write negative 2 as a factor? As x plus 2. And then the rest just follows down, x squared minus 3 and plus 0. But I'm not going to write plus 0. You'll also notice I didn't bother writing plus 0x. Because at this point, this is what we have. Now, are we done?
No,
Why not no?
because there's still a square, it's still the x.
Yeah, it's still a quadratic in there. We have a square. We want to get all the way to x, x, x. We want 3 factors. Because it's x to the power of 3, so we want 3 factors. How does that last part factor? X what? Now, I don't think I've shown you this cute and clever trick. This is really neat. I know you all know about the difference of squares if it's a square number. And if it's 25, then what does it become? Yeah, x plus 5, x minus 5. Now watch how cool this is. If you actually wanted to memorize the real formula, you take exactly that number, and the real formula is x plus root that number, x minus root that number. And it just so happens, okay, this is the real formula, that because the square root of 25 is something you can do, you change it and you write x plus 5, x minus 5. Okay, but the actual formula, like if I just take x squared minus a, okay, a can be anything, then it actually becomes x minus root a, x plus root a. So in the case of x squared minus 3, what do we have? Yeah. Yeah, that's it. This is the general formula. Okay, difference of squares. It's all good to memorize when you have a square and a square. It's easy. If it's not a square, then it's x minus root that number, x plus root that number. And that's more of a general strategy.
I was thinking, if you take one of those, make it equal to 0, isn't that the same thing as just square root side? Like, I bring
Yes.
yeah.
Absolutely. That's really good. Higher level. Let's remember that if we want to find the x-intercepts of the x squared minus 3, remember, how do you find an x-intercept? You set it equal to 0. Watch this. So if you have x squared minus 3, you want to know how to factor it. You set it equal to 0, move the 3 over, square root both sides, and you have x equals plus or minus root 3. Therefore, the x-intercepts are positive root 3 and negative root 3. On a graph, if the x-intercept is positive root 3 or negative root 3, what factor would I write down? For the plus root 3, I'd write down the factor x minus root 3. And for the negative root 3, x plus root 3. And you notice you still get the same answer. Yeah, really good. Yeah, thanks for bringing that up. You don't even have to know this. You can just fall back on the old standby. And if you want to know an x-intercept, if you want to factor something, you just set it equal to 0 and solve for x. That's really interesting. That's really cool. Okay, so what's our final answer? X plus root 3, x minus root 3. It doesn't matter what order you write it in. Though to Hector's point, it would be nice if they were written in order from left to right. And so now, let's finish our graph. Everyone start a nice new graph. I know I kind of started the graph at the beginning, but forget that. That was just scratch work. Let's make a good graph. So, first of all, the square root of 3 is 1.7-ish. It's really 1.73205968923. I don't have that memorized. I just made that up. But it's 1.7 something. So where are all of our x-intercepts? We have an x-intercept all the way over at -2. So that's for sure one of them. And then I have an x-intercept at plus or minus 1.7. So I have another dot right there and another dot over here right there. Now I'm going to go ahead and label it -√3 and +√3. But I know I put the dots in the right spot because I did it on my calculator and it's 1.7. Okay, so we have our 3 x-intercepts. Where's our y-intercept? Now remember, we had information in the given problem. The y-intercept was -6. The end behavior is x cubed. So our y-intercept is -6. The end behavior is a cubic. So that's just that shape. So you go to the far right-hand x-intercept and put your tail going up. Far left-hand x-intercept, tail coming down. And then each one of these factors has a power of 1, so they're all a slice. They're not a bounce, they're a slice. And so you do slice, slice, slice.
Eat a pizza.
Eats a pizza. Hey man, I like Eats a Pizza. Does anyone, do those places still exist? Oh man, I used to love
I
Eats a
think
Pizza.
Red Devil. I don't know.
It's like a buffet.
Eats a Pizza is a buffet of some of the lowest quality, tastiest pizza you'll ever have.
I used
Okay,
to go there with my
then
dad.
Caesar's Palace.
What do they have? All you can eat pizza or a buffet? I love buffets. All right. Well,
You
folks.
go to Las Vegas a lot?
No,
Okay.
I've been, but I don't gamble. Okay,
Yeah, I'm doing good buffet.
folks, you all did really well. So we're going to skip number 9. We are going to do number 10, and then we're going to do a couple more problems, and that brings us to section, I think next is 3.3. I kind of wish that we had finished that because it's the end of the week, so now I can't assign 3.2 for you for homework. But for sure, due Monday is 3.0 and 3.1. I think you should start 3.2. And then when you come back next week, we'll pick up from where we left off. Okay, now I bet you all want your tests. By the way, does anyone know where Omar is today? Where's Omar? I sure hope he's coming back. I had to admit, I feel like some sort of like damaged person. Like anytime someone's absent, I'm like, are they coming back? Like there's no good reason for me to worry like that, and yet that's what I think. I'm like, oh, I hope they're coming back.
Use it for
Yeah, no, these are yours. Yeah, you keep these forever. Take them home. Now, honestly, my biggest recommendation is you go home. You look at every single problem and you figure out how to do it. So if you miss a problem, I don't care if you miss 1 problem or 10 problems, you go home and you figure out how to do it. And then you're all the more prepared for your final exam. Because your goal, here's your real goal with any exam you ever take in your whole life. You go in and you take the exam. I don't care what you got. You got an 80%, you got a 60%, you got a 100, well, a 99%. You should go right back home and study it. Such that if your teacher let you take the test again, what would you get? 100. That's always your attitude towards a test. You get it back, you study it well enough that if you took it again, you could get 100. Because honestly, what if one day your teacher came up to you and was like, hey, you want to take the test again? I'll let you. You're like, oh, I totally didn't study it. I'm not ready. You just miss out on that huge life gift. Yeah, go
All I
ahead.
had to do was erase this.
What?
All I had to do was erase this.
No, because the equation is y equals 4. That's a coordinate.
Yeah, but if I would have
Yeah, exactly. So what you have here is the equation is x equals -2. That, the coordinate of the x-intercept. Yeah, that's what no, you did. It said give the slope.
Oh, okay.
And unfortunately, these two slopes are switched.
Okay.
This is an undefined slope, and this is a zero slope. So those have values switched in the interview equation. You have that like this horizontal. Yeah, and in fact, I also like here, if you did set f of x equals 0, right, so you're saying f is 0, so that would describe a y-intercept, but this line doesn't have a y-intercept. And this you're describing an x-intercept, this line doesn't have an x-intercept. So there's just some things that we're mixing up. Yeah. Folks, please come ask me questions. Review your test. Go home tonight. Review your test, and then either email me or come back during office hours and ask me any questions you like. I would really like to help.
Yeah, I thought I missed a lot more than because I caught up like with 3-0, 3-1.
As well, if you guys like to come see me act
Oh,
as well.
Yeah, by the way, folks, please come see Lee, because like right now, Lee has office hours.